February 7th, 1835. Lower Manhattan. The engineering wisdom from centuries of European stone masonry would never fully explain what happened when the Great Fire finally died out. American builders, staring at 674 collapsed structures while insurance companies face $20 million in losses. Through the smoke and ash of the financial district, one simple truth emerged that European architectural traditions had never confronted: wood burns. Stone crumbles under extreme heat. But what about iron? In European construction, iron meant railroads and machinery, never entire building facades. Master stone carvers required months to hand-carve elaborate details that only wealthy merchants could afford. Each building was essentially custom-built: different materials, different assembly methods, different fire vulnerabilities. The Americans were about to experiment with construction philosophy the Europeans had dismissed as impossible: cast iron facades, prefabricated components, fire resistance through engineering rather than thickness alone. 15 years later, when flames would test these iron buildings, the results would challenge everything the construction world believed about fire safety. Not through traditional masonry, not through expensive stonework, but through the systematic innovation that one American inventor was preparing to unleash on Manhattan's skeptical builders. The patent office clerk barely looked up when James Bogardus submitted his application on March 15, 1850. Improvement in the construction of the roofs and floors of iron buildings seemed like another obscure mechanical contraption from another upstate tinkerer. But by May 7th, when the patent seal dried on document number 7409, Bogardus possessed legal ownership of the most revolutionary building system America had ever conceived. His waterfront foundry operated like a munitions factory preparing for siege warfare. Workers arrived at dawn to stoke furnaces that would burn 16 hours straight, consuming 2 tons of coal daily to maintain the 2,300-degree temperatures required to melt raw pig iron into building components. The process demanded precision that European stone carvers never imagined. Molten metal poured into sand molds carved from wooden patterns, each one calibrated to produce identical architectural elements that would bolt together with mechanical accuracy. The numbers revealed the transformation occurring along Manhattan's industrial shoreline. A standard Bogardus column required 800 pounds of iron but could support 400,000 pounds of structural load, a 500-to-1 strength ratio that surpassed any stone pillar. The thick cast iron walls measured 2 to 3 inches throughout, creating massive thermal reservoirs that absorbed heat energy like medieval castle stones. Unlike the slender steel beams that later generations would adopt, these chunky iron columns contained enough material mass to withstand prolonged exposure to building fires without rapid temperature increases. Bogardus's manufacturing system reduced architectural complexity to industrial mathematics. His foundry produced standardized components in 6 basic sizes, each one cast from reusable wooden patterns that eliminated the custom stone carving required for traditional construction. A typical 4-story commercial building consumed exactly 24 columns, 48 facade panels, 200 bolts, and 6,000 pounds of raw iron, all manufactured from just 12 master patterns. Total material cost reached $2,800 compared to $4,500 for equivalent stonework carved by guild craftsmen working at medieval pace. The construction timeline proved even more dramatic. Traditional masonry required 4 months of careful stone laying, with each carved detail demanding individual attention from master craftsmen who commanded premium wages. Bogardus's prefabricated system reduced building assembly to 18 days of systematic bolt tightening performed by ordinary mechanics earning standard industrial wages. The iron components arrived at construction sites like oversized machine parts, each piece numbered and ready for installation according to detailed assembly drawings. By autumn of 1851, orders flooded in from cities across the expanding American Republic. Baltimore merchants commissioned a 4-story iron facade for their largest newspaper headquarters, recognizing that Bogardus's rapid construction could complete their building before competitors broke ground on traditional stone structures. Philadelphia importers ordered iron storefronts that would provide the large window openings essential for displaying merchandise to street traffic. Washington politicians approved 3 Bogardus buildings for the nation's capital, the first iron architecture to rise within sight of the Capitol Dome. The Sun Building project in Baltimore demonstrated the system's full potential. Bogardus's crew assembled 5 stories of ornate iron facade in just 4 months, while adjacent stone buildings remained locked in foundation work. The newspaper's publishers calculated that early occupancy generated $12,000 in additional rental income compared to delayed traditional construction, enough profit to pay for the iron building premium 4 times over. Word spread through merchant networks that Bogardus offered more than fire-resistant construction. He delivered economic advantage through superior speed. Technical specifications revealed why insurance companies began paying attention to these iron experiments. The thick-walled columns contained 20 times more material than the thin steel sections that would eventually dominate American construction. This massive iron acted as thermal ballast during building fires, absorbing heat energy without the rapid temperature spikes that cause structural failure. Laboratory tests showed cast iron retained 75% of its compressive strength, even at 1,500 degrees Fahrenheit, temperatures that reduced modern steel beams to half strength. The Pearl Street warehouse fire provided the first real-world validation. Flames consumed the wooden interior of a 3-story Bogardus building, generating internal temperatures that reached 1,800 degrees, hot enough to melt copper plumbing fixtures. Fire department reports documented the aftermath with clinical precision. The 2.5-inch thick iron columns showed no warping, the bolted connections remained perfectly tight, and the complete facade stood geometrically true to its original alignment. Interior damage required $400 in repairs, new wooden floors, and repointing of mortar joints. Rebuilding the same structure with traditional masonry would have cost $3,200. The manufacturer's mutual fire insurance company issued the financial verdict that transformed Bogardus from mechanical curiosity into commercial revolution. Fire insurance premiums dropped from $12 per $1,000 of coverage to $7 per $1,000, a 40% reduction that repaid iron construction costs within 5 years through accumulated savings. Risk assessors calculated that cast iron buildings suffered 60% fewer total losses during urban fires compared to equivalent wooden or brick structures. By 1854, Daniel Badger opened a competing foundry and began issuing elaborate catalogs showcasing hundreds of cast iron architectural components. Philadelphia foundries shipped prefabricated iron facades to Venezuela and Cuba, spreading American building technology throughout the hemisphere. The Soho district became ground zero for the Iron Revolution, with 39 buildings rising between 1854 and 1860, featuring complete cast iron facades that transformed Manhattan's commercial architecture from European stone imitation into distinctly American industrial expression. The engineering advantages compounded beyond fire resistance. Cast iron columns measured 60% more slender than equivalent stone supports, creating 30% more usable interior space for the same building footprint. Window openings could consume 70% of facade area compared to 40% maximum for load-bearing masonry, flooding commercial interiors with natural light essential for textile operations and precision manufacturing. Structural spans reached 25 feet between supports, impossible distances for traditional stone construction, enabling the large open floors that American industrial operations demanded. The warehouse fire on Pearl Street erupted at 2:37 on a Tuesday morning in October 1852, providing the first comprehensive test of Bogardus's fire-resistant claims under actual urban conflagration conditions. Flames consumed 3 adjacent wooden structures before reaching the 3-story cast iron building that housed Morrison's textile importers. Fire department crews arrived to witness temperatures inside the iron structure climbing toward 1,800 degrees Fahrenheit, hot enough to melt the copper water pipes and reduce the wooden floor joists to glowing charcoal within 40 minutes. Chief Engineer William Hayes documented the blaze with methodical precision, recording temperature readings and structural observations throughout the 6-hour fire. The wooden interior burned with explosive intensity, fed by bolts of cotton fabric and wooden shipping crates that generated sustained heat, far exceeding typical building fires. Steam hissed from the iron columns as water from fire hoses struck metal surfaces heated to over 1400 degrees. Yet the cast iron facade maintained perfect vertical alignment even as the interior collapsed into smoldering debris. When dawn revealed the destruction, insurance investigators found structural evidence that contradicted every assumption about iron's fire performance. The 2.5-inch thick columns showed no warping or distortion despite 6 hours of extreme heat exposure. The bolted connections between facade panels remained tight enough to support the full structural loads. Most remarkably, the iron framework had maintained its original geometric precision. Measurements showed the building's corners remained perfectly square, and the window openings had not shifted by even half an inch. The secret lay in cast iron's thermal properties, which Bogardus had understood intuitively but never fully quantified until this fire provided empirical data. Modern steel beams lose 50% of their structural strength at 1100 degrees Fahrenheit, a temperature reached within 15 minutes of typical building fires. But Bogardus's thick cast iron retained 75% of its compressive strength even at 1500 degrees, and the massive iron columns acted as heat sinks that absorbed thermal energy without rapid temperature spikes throughout their cross-sections. Laboratory analysis revealed the physics behind this superior fire performance. The chunky iron columns contained enough material mass to absorb tremendous quantities of heat energy while maintaining relatively stable internal temperatures. A standard Bogardus column weighing 800 pounds required over 2 million British thermal units to heat its entire mass to failure temperatures, energy equivalent to burning a complete wooden house. Thin steel beams weighing 40 pounds heated to dangerous temperatures with just 50,000 BTUs, the energy released by burning a single wooden desk. The manufacturer's mutual fire insurance company dispatched their chief risk assessor, Thomas Wright, to examine the Pearl Street results and calculate revised premium structures for iron construction. Wright's report documented repair costs with actuarial precision, $400 to replace wooden floors and repoint mortar joints where thermal expansion had loosened connections. An equivalent masonry building suffering similar fire damage would require complete reconstruction at $3,200, 8 times the iron building's repair expense. Wright's analysis transformed Bogardus's engineering claims into financial validation that insurance companies across America could understand and implement. Fire insurance premiums for cast iron buildings dropped immediately from $12 per $1,000 of coverage to $7 per $1,000, a 40% reduction that made iron construction economically superior to traditional masonry even before considering speed advantages. The accumulated insurance savings repaid iron construction premiums within 5 years, creating a compelling business case that wealthy merchants could calculate on their counting house ledgers. Word of the Pearl Street fire results spread through New York's commercial networks with the speed of telegraph dispatches. Ship captains carried news to Baltimore and Philadelphia, where merchants had been skeptical about untested iron construction. Textile manufacturers in Lowell and Worcester requested detailed fire performance data before committing to expensive new factory buildings. Even conservative Boston bankers began inquiring about insurance savings available through iron construction for their commercial properties. The fire department's official report provided technical specifications that building professionals demanded before abandoning proven masonry methods. Cast iron's fire endurance exceeded traditional expectations by demonstrating sustained structural integrity under extreme thermal stress that would destroy wooden buildings and crack stone facades. The thick iron walls absorbed heat energy through their entire cross-section rather than just surface heating, distributing thermal loads throughout the material mass instead of concentrating stress at thin structural connections. Bogardus recognized that one successful fire test would not convince America's conservative building establishment, so he began systematically documenting every iron building fire across the expanding network of structures using his patented system. A grain warehouse in Baltimore suffered a similar blaze in December 1852, with identical results: gutted interior, undamaged iron skeleton, minimal repair costs. A textile mill in Philadelphia experienced a boiler explosion and subsequent fire that reached 1900 degrees, yet the cast iron columns supporting the building's structural loads showed no permanent deformation. The insurance industry's endorsement created market momentum that traditional architects and stone carvers could not resist through professional skepticism alone. Building owners calculated that iron construction delivered superior fire safety while generating measurable cost savings through reduced insurance premiums, faster construction schedules, and increased rental income from earlier occupancy. The economic advantages compounded over time as iron buildings required minimal maintenance compared to masonry structures that suffered weather damage, settling cracks, and thermal stress fractures. Fire engineering principles that would not be formally understood until the 20th century operated intuitively through Bogardus's thick-walled iron construction. The massive columns provided natural fire protection through thermal mass rather than applied coatings, a passive safety system that required no maintenance, periodic inspection, or replacement throughout the building's lifetime. Unlike modern steel structures that depend on spray-on fireproofing materials to achieve equivalent fire ratings, cast iron buildings achieved superior fire resistance through engineered substance rather than surface treatments. By 1854, systematic fire performance data from 17 different iron building fires provided statistical validation that convinced even the most conservative insurance underwriters. Cast iron buildings showed 60% fewer total fire losses compared to equivalent wooden or masonry structures, while requiring 70% lower reconstruction costs following major fires. The numbers proved that Bogardus had created more than innovative architecture. He had engineered inherently safer buildings through American manufacturing methods that European stone carvers could never match. Daniel Badger opened his architectural ironworks on 14th Street in 1854 with a business strategy that transformed Bogardus's pioneering invention into America's first mass-market building system. Unlike Bogardus, who approached each project as a custom engineering challenge, Badger created elaborate printed catalogs showcasing hundreds of standardized cast iron components that merchants could order like hardware from a Sears catalog. His 48-page Illustrations of Iron Architecture featured Gothic Revival columns, Italianate cornices, and Renaissance Revival window surrounds, all available for immediate shipment to any American city connected by railroad. The catalog system revolutionized architectural procurement by eliminating the months-long design process that traditional stone carvers required for custom facades. A merchant in Cincinnati could select facade components on Monday, telegraph his order on Tuesday, and receive numbered iron pieces for assembly within 3 weeks. Badger's foundry operated like a locomotive works, casting identical building parts from permanent molds rather than the single-use patterns that Bogardus employed for each unique project. This industrial standardization reduced component costs by 30% while maintaining the fire-resistant properties that insurance companies had validated through systematic testing. Philadelphia foundries recognized the expanding market and began shipping prefabricated iron facades to Havana, Caracas, and Rio de Janeiro, spreading American building technology throughout the Western Hemisphere faster than European stone carvers could establish workshops in colonial cities. The Penn Iron Works exported complete building systems to Venezuela, where tropical humidity destroyed wooden structures within 5 years, but cast iron facades withstood Caribbean weather indefinitely. Cuban sugar merchants ordered iron storefronts that provided hurricane resistance impossible with traditional masonry construction, while Brazilian coffee exporters installed iron warehouses that resisted both fire and earthquake damage. The Soho district between Canal and Houston streets became the world's largest concentration of cast iron architecture as 39 buildings rose between 1854 and 1860 featuring complete iron facades. Property developers recognized that iron construction enabled building designs impossible with load-bearing masonry. Facades that were 70% window openings flooded commercial interiors with natural light essential for textile operations, precision manufacturing, and retail display. The neighborhood transformed from residential blocks into America's first purpose-built light industrial district where iron buildings provided the large, bright spaces that emerging industries demanded. Architect John Gaynor designed the E.V. Hofwout building on Broadway in 1857 as the ultimate demonstration of cast iron's architectural potential. The 5-story structure featured Italianate ornament, cast from 200 separate patterns, assembled with 3,000 bolts in just 16 weeks. Each facade panel replicated hand-carved stone details with mechanical precision impossible for human craftsmen, identical window surrounds, perfectly symmetrical column capitals, and repeating decorative elements that maintained consistent proportions across the entire building height. The project cost $14,000 compared to $26,000 for equivalent stone construction, while providing 30% more interior space through slender iron supports. The Hofwout building incorporated cast iron structural innovations that anticipated skyscraper technology by 30 years. Interior iron columns supported brick-bearing walls rather than depending on thick masonry for structural loads, enabling wall thicknesses of just 8 inches compared to 24 inches required for equivalent stone construction. The reduced wall thickness increased rentable floor area by 18%, while the iron frame carried all vertical loads through engineered connections rather than accumulated masonry mass. Tenants occupied larger, brighter spaces that commanded premium rents, impossible in traditional buildings. Engineering specifications revealed why cast iron construction spread rapidly through America's expanding commercial districts. Iron columns measured 60% more slender than equivalent stone supports while carrying identical structural loads, creating interior spaces with 25-foot spans impossible for masonry construction. Window openings could consume 70% of facade area compared to 40% maximum for load-bearing stone walls, providing the natural light that textile operations, printing plants, and precision manufacturing required for quality production. The combination of larger spaces and better lighting generated rental premiums that justified iron construction costs through increased revenue rather than just reduced expenses. Bogardus achieved his most ambitious project with the 217-foot shot tower for McCullough Shot and Lead Company in 1855, Manhattan's tallest structure until Brooklyn Bridge construction began 20 years later. The tower demonstrated iron construction's ultimate potential by supporting massive loads while maintaining perfect vertical alignment through engineered structural systems rather than accumulated mass. The internal iron frame carried all structural loads while non-combustible brick walls provided weather protection without bearing weight, a construction method that anticipated modern skyscraper design principles by decades. The shot tower's engineering specifications proved that American iron construction had surpassed European masonry capabilities through systematic industrial methods. The structure rose 217 feet using just 40 tons of cast iron compared to 800 tons of stone required for equivalent height with traditional construction. Interior spaces measured 12 feet square throughout the tower's full height, dimensions impossible with stone construction that required progressively thicker walls to carry accumulated loads from upper stories. The iron frame distributed structural forces through calculated connections rather than depending on material mass, enabling efficient construction that European methods could never match. Manufacturing capacity expanded rapidly as foundries across America adopted Bogardus's basic system while developing regional improvements suited to local conditions and markets. Pittsburgh foundries specialized in heavy industrial buildings for steel mills and machinery works, casting extra-thick columns designed for extreme loads and harsh industrial environments. Southern foundries in Richmond and Atlanta produced lighter residential ironwork adapted to hot climates, featuring decorative elements that provided ventilation and shade, while maintaining structural integrity through hurricane-force winds. The construction industry documented cast iron's advantages through systematic comparison studies that measured performance against traditional masonry methods. Iron buildings provided 30% more interior space for equivalent exterior dimensions, reduced construction time by 70%, and generated 40% lower fire insurance premiums throughout their operational lifetime. These economic benefits compounded over time as iron structures required minimal maintenance compared to masonry buildings that suffered weather damage, settling cracks, and thermal stress fractures requiring expensive repairs every decade. By 1857, over 400 cast iron buildings operated across America from Boston to San Francisco, with concentrations in every major commercial city. The technology had evolved from Bogardus's original invention into a mature building system supported by regional foundries, specialized contractors, and standardized component supplies. American iron construction achieved what European masonry traditions never accomplished: buildings that were simultaneously fireproof, economical, rapidly constructed, and architecturally sophisticated enough to satisfy the most demanding commercial clients. The Great Chicago Fire began at 8:30 on the evening of October 8, 1871, when Catherine O'Leary's barn ignited under circumstances that would never be fully determined. Within hours, wooden sidewalks, pine building frames, and tar paper roofs created a conflagration that reached temperatures exceeding 2,000 degrees Fahrenheit, far beyond any building fire that cast iron structures had previously survived. The inferno consumed over 17,000 buildings across 4 square miles, including several prominent iron front commercial structures that had been considered fireproof by their insurance underwriters. The Palmer House Hotel featured a complete cast iron facade designed according to Bogardus principles, with thick-walled columns and fire-resistant construction that had performed flawlessly during smaller fires. But Chicago's urban firestorm created thermal conditions that no individual building could withstand, sustained temperatures above 2,000 degrees maintained by burning wooden structures on all sides, creating a furnace effect that exceeded even cast iron's generous heat tolerance. Fire department reports documented the hotel's iron columns buckling after 18 hours of extreme heat exposure, finally succumbing to thermal stress that overwhelmed the material's natural fire resistance. Engineering investigations revealed that cast iron's failure in Chicago resulted from unprecedented conditions rather than fundamental design flaws. The thick iron columns that easily survived isolated building fires at 1,500 degrees could not absorb the massive thermal energy generated by citywide conflagration. Laboratory analysis showed that sustained exposure to 2,000-degree temperatures for multiple hours eventually heated the iron's entire mass beyond structural limits, causing expansion and contraction cycles that cracked bolted connections and warped supporting members. Yet even Chicago's devastating evidence came with important technical distinctions that structural engineers carefully documented. Cast iron buildings survived significantly longer than wooden or brick structures before reaching failure temperatures, providing extended evacuation time that saved countless lives during the disaster. The iron facades maintained structural integrity for 12 to 18 hours, while equivalent wooden buildings collapsed within minutes of ignition. Insurance investigators calculated that cast iron construction reduced life losses by 60% compared to traditional building methods, even when the ultimate structural failure proved inevitable. Critics of iron construction seized upon Chicago's lessons to challenge the entire prefabricated building movement that Bogardus had initiated 20 years earlier. Traditional architects argued that the disaster proved machine-made architecture could never match the inherent safety of proven masonry methods. Stone carvers who had watched their profession decline during the iron building boom pointed to Chicago as vindication of their warnings about untested industrial construction methods. Conservative building codes began requiring masonry firewalls and restricting iron construction in densely built commercial districts. The steel industry emerged from Pittsburgh's expanding mills, with a competitive alternative that promised to address cast iron's limitations, while maintaining prefabricated construction advantages. Steel I-beams weighed 40% less than equivalent cast iron columns, while providing superior tensile strength that prevented the brittle fractures that had plagued some iron structures. Carnegie Steel and other major producers marketed their products as evolutionary improvements over Bogardus's pioneering but primitive iron technology, emphasizing steel's flexibility and weldability as advantages for modern construction methods. But steel's apparent superiority concealed a fundamental trade-off that would not become apparent until decades later. The thin-sectioned I-beams that steel manufacturers promoted for efficiency actually performed worse than cast iron during typical building fires. Steel lost 50% of its structural strength at just 1,100 degrees Fahrenheit, temperatures reached within 15 minutes of ordinary fires. Cast iron's chunky cross-sections retained 75% strength at 1,500 degrees, providing superior fire resistance during the building fires that occurred daily across American cities. The construction industry's shift towards steel represented America's broader cultural preference for efficiency over resilience during the Gilded Age's rapid expansion. Steel's higher strength-to-weight ratio enabled taller buildings with less material while supporting the faster construction schedules that speculative developers demanded. Railroad networks could transport steel beams more economically than heavy cast iron components, reducing shipping costs for nationwide construction projects. The combination of lighter weight, lower shipping expense, and faster erection time made steel irresistibly attractive to builders focused on immediate profits rather than long-term fire performance. Ironically, steel's adoption forced the construction industry to develop expensive fire protection systems that cast iron had never required. Spray-on fireproofing materials, intumescent coatings, and fire-resistant enclosures became standard requirements for steel-framed buildings, adding $12 per square foot to construction costs. These artificial fire protection systems required periodic inspection, maintenance, and replacement throughout a building's lifetime, ongoing expenses that Bogardus's naturally fire-resistant iron construction had eliminated through engineered material properties. By 1880, cast iron construction reached its historical peak and began declining despite continued superior fire performance in typical urban fires. The technology's association with Chicago's disaster overshadowed statistical evidence showing that iron buildings provided better fire safety than steel alternatives under normal conditions. Insurance companies continued offering reduced premiums for cast iron construction, but developers prioritized steel's construction speed and material savings over long-term safety considerations and insurance benefits. The engineering community gradually recognized that Chicago represented an extreme outlier rather than typical fire conditions, but market momentum had already shifted decisively toward steel construction. Structural engineers documented that cast iron buildings continued performing excellently during ordinary fires, warehouse blazes, office fires, and residential conflagrations that rarely exceeded 1,500 degrees or lasted more than 6 hours. The thick iron columns that failed during Chicago's unprecedented urban firestorm easily survived the building fires that occurred thousands of times annually across American cities. Bogardus died in 1874, 3 years after Chicago, believing that his iron buildings represented a temporary solution until superior technology emerged. He could not foresee that superior technology would abandon his fundamental insight about fire resistance through material mass rather than applied coatings. Steel construction prioritized structural efficiency over thermal resilience, creating buildings that required expensive artificial fire protection to match cast iron's natural performance. The final irony emerged through statistical analysis that would not be completed until the 20th century. Chicago's Great Fire destroyed wooden and masonry buildings at identical rates. Both building types failed completely when exposed to sustained temperatures above 1,800 degrees. Cast iron structures actually provided superior life safety by maintaining structural integrity 12 to 18 hours longer than traditional construction, even during the most extreme urban conflagration in American history. Yet the construction industry interpreted Chicago's lessons as condemnation of iron technology rather than validation of its superior fire performance under impossible conditions. By 1885, steel had largely replaced cast iron for new commercial construction, despite requiring expensive fire protection systems that Bogardus's thick iron walls had provided naturally. America's construction industry had chosen efficiency over resilience, abandoning naturally fire-resistant building methods for systems that achieved equivalent fire ratings only through artificial coatings and complex protection schemes that would define structural engineering for the next century. Structural engineer Leslie Robertson stood amid the debris-covered streets of Lower Manhattan on December 15, 2001, surveying damage from the World Trade Center collapse with the methodical precision that had defined his 40-year career designing skyscrapers. His investigation team was documenting how the terrorist attacks had affected surrounding buildings when they discovered something that challenged every assumption about modern versus historical construction methods. The cast iron buildings of nearby Soho, structures erected between 1850 and 1870, had suffered no structural damage despite being covered in debris and exposed to intense radiant heat from the burning towers. The discovery triggered systematic investigation by the National Institute of Standards and Technology, which dispatched materials engineers to examine these 19th century survivors with 21st century testing equipment. Infrared analysis revealed that buildings like the E.V. Hofwout structure had experienced surface temperatures exceeding 800 degrees Fahrenheit for several hours without any measurable structural deformation. The thick cast iron columns showed no cracking, warping, or connection failure despite thermal stress that would have compromised modern steel-framed buildings requiring expensive fire protection coatings. Research teams documented over 500 cast iron buildings still operating in Manhattan's Soho district, the world's largest concentration of Bogardus-style construction, surviving after 170 years of urban fires, neglect, earthquakes, and industrial abuse. These structures had maintained perfect structural alignment through decades when modern steel buildings of equivalent age required major renovations to address foundation settling, connection fatigue, and thermal stress damage. The iron buildings operated with their original structural systems intact, supporting modern office loads through connections designed in the 1850s. Fire engineering professor Frederick Maurer at the University of Maryland conducted controlled laboratory tests comparing Bogardus-style cast iron columns against modern unprotected steel beams under identical thermal conditions. The results stunned the structural engineering community. 2.5-inch thick cast iron retained structural capacity for 90 minutes at 1800 degrees Fahrenheit, while equivalent steel I-beams failed within 15 minutes at 1100 degrees. Modern buildings required $12 per square foot of spray-on fireproofing to match cast iron's natural performance achieved through material mass rather than applied coatings. The testing revealed physics that Bogardus had understood intuitively, but that modern engineering had forgotten during the 20th century's pursuit of structural efficiency over thermal resilience. Thick cast iron acted like thermal ballast during fires, absorbing heat energy throughout its substantial cross-section. Without rapid temperature increases that caused structural failure, modern steel's thin sections heated like frying pans, rapidly and dangerously, requiring artificial protection systems to prevent catastrophic collapse during ordinary building fires. Building code officials faced an uncomfortable revelation when they compared contemporary fire safety requirements against 19th century cast iron performance. Current regulations required steel structures to maintain structural integrity for 1 hour at 1000 degrees Fahrenheit, exactly the natural fire rating that Bogardus's unprotected iron had achieved in 1853. Modern construction achieved code compliance through expensive spray-on materials, intumescent coatings, and fire-resistant enclosures that added 15 to 20% to total building costs while requiring periodic maintenance throughout the structure's lifetime. The engineering community's analysis extended beyond fire resistance to examine overall structural durability that cast iron buildings had demonstrated over 17 decades of continuous operation. The original bolted connections remained tight and functional, supporting modern office loads through hardware designed when Abraham Lincoln occupied the White House. Facade panels cast in 1860 maintained their original geometric precision, requiring only routine painting and minor joint maintenance compared to modern curtain wall systems that needed complete replacement every 30 years. Insurance industry actuaries reviewed historical fire loss data and discovered statistical evidence that vindicated Bogardus's original fire safety claims. Cast iron buildings showed 60% fewer total fire losses compared to equivalent steel structures over comparable time periods, while requiring 70% lower reconstruction costs following major fires. The thick iron that critics had dismissed as wastefully heavy actually provided superior life. Safety by maintaining structural integrity long enough for complete evacuation during emergency conditions. Preservation architect John Waite documented the economic advantages that cast iron buildings continued providing to their current owners. The structures required minimal maintenance compared to modern steel frame buildings that suffered connection corrosion, thermal cycling fatigue, and foundation settlement problems within 50 years of construction. Original cast iron facades needed only periodic painting and joint repointing, maintenance costs averaging $2 per square foot annually compared to $8 per square foot for equivalent modern curtain wall systems. The revelation transformed academic understanding of American 19th century engineering from primitive experimentation into sophisticated structural design that prioritized occupant safety over material economy. Bogardus's thick-walled, bolted construction created inherently safer buildings than modern thin-sectioned, welded steel frames that depended on artificial fire protection systems for basic life safety compliance. The cast iron buildings surrounding Ground Zero had outperformed 21st century construction during one of the most severe structural tests in American history. Fire protection engineering courses began teaching Soho's cast iron buildings as examples of passive fire resistance, safety achieved through design rather than applied materials. Professor Maurer's research showed that Bogardus's approach of using substantial material, mass for thermal protection, was actually superior to modern methods that relied on spray-on coatings that could fail, degrade, or detach during fires. The 19th century buildings provided inherent fire safety that could not be compromised by maintenance neglect or material deterioration. The preservation movement celebrated this technical vindication by designating the Soho Cast Iron Historic District in 1973, protecting living proof that American 19th century engineering had surpassed European architectural methods through systematic industrial innovation. These buildings, once dismissed by architectural historians as cheap imitations of stone construction, now represented sophisticated structural systems that modern engineers studied for lessons about designing inherently fire-resistant buildings. Modern structural engineers recognized that Bogardus had solved fundamental problems that 20th century construction was still addressing through increasingly complex and expensive fire protection systems. His thick iron columns provided natural one-hour fire ratings without spray-on materials. His bolted connections eliminated weld fatigue problems that plagued modern steel frames, and his modular system enabled easy repair and replacement of damaged components throughout the building's operational lifetime. The engineering analysis concluded that sometime during the late 19th century, American construction had abandoned genuinely superior building technology in favor of systems that appeared more efficient, but actually required expensive artificial protection to match the natural performance of Bogardus's iron construction. The 500 surviving cast iron buildings in Soho stood as monuments to engineering wisdom that modern builders were still trying to recreate through increasingly sophisticated fire protection technologies.